Welcome to this tech news update and explainer, where we're breaking down an absolute monumental shift happening in web technology right now. We are talking about WebGPU. This is the upgrade that fundamentally changes what your web browser is actually capable of doing. If you've been following web dev for a while, you know the browser has historically been, well, kind of fenced off from the raw bare metal power of your device's hardware. But as we look at late 2025 and into 2026, yeah, that fence has been completely torn down. So I want you to start by just asking yourself this. What if you could run complex artificial intelligence models directly on your device? We're talking zero server costs, zero latency, and absolute privacy. No API keys to manage, no sensitive data ever leaving your machine, just pure native acceleration happening right there inside the web page you just clicked open. Sounds a bit like a distant dream, right? Well, actually, it's not. It is the reality we're stepping into today. And look, this isn't just some experimental feature hidden behind obscure developer flags that you have to toggle on. No, after 8 long, grueling years of specification work by the W3C GPU for the Web Working Group, Chrome, Firefox, Safari, and Edge, they all ship WebGPU by default now. It has officially hit critical mass. WebGPU is the modern cross-platform default deployed across all major browsers, so developers can finally write code with the absolute confidence that everyday users can actually run it today. Section 1, the bottleneck. Let's look at the limitations of WebGL to really understand the frustrating limits of the technology we're finally leaving behind. For over a decade, we've relied heavily on WebGL. And don't get me wrong, it was revolutionary at the time, but it's severely bottlenecked by a single-threaded CPU model that is literally frozen to 2011 specifications. With WebGL, every single draw call has to execute sequentially, one after the other. So you might have this incredibly beefy modern GPU, but your scene maxes out because your CPU simply cannot feed commands to the graphics card fast enough. Your GPU might be sitting there at, say, 40% utilization, completely idle, just twiddling its thumbs, waiting for instructions. WebGPU changes the game entirely. It allows developers to prepare rendering commands across all available CPU cores simultaneously. It's a massive difference. WebGPU isn't just an update, it's a complete architectural upgrade. It wasn't built on those aging OpenGL standards. Instead, it's modeled directly after modern native APIs. Think Vulkan, Metal, Direct3D 12. This gives developers granular, explicit control over GPU memory and pipeline state. And what's really fascinating here is the immediate real-world impact this has in mobile devices. Because you have substantially reduced CPU overhead, you get vastly improved battery efficiency. Your phone literally doesn't have to work as hard. That means less heat generation, which prevents that awful thermal throttling that used to just ruin mobile web rendering. Plus, it has an extensible design, meaning as GPU hardware inevitably evolves over the coming years, WebGPU can expose those new capabilities without anyone needing to do a complete rewrite. Okay, Section 2, the secret weapon. Let's move over to the technical core and see how compute shaders build into an entirely new capability for the web. The real game changers here are compute shaders. These essentially turn your graphics card into a massive parallel processing beast for any data, not just graphics. Under the old WebGL, if you wanted to run, say, a complex physics simulation, you had to run it on the CPU, or you had to try and hack it into a rendering pipeline. People called that ping-pong rendering, and let me tell you, it was highly restrictive and incredibly clunky. But compute shaders in WebGPU, they let you run arbitrary algorithms natively on the thousands of cores inside your GPU. This is unlocking massive leaps in things like scientific visualization, allowing researchers to interactively render terabytes of simulation data directly in their browser. To put that power into perspective with a more common scenario, let's look at particle systems. If you try to updating a 10,000 particle simulation in WebGL on the CPU, it might take roughly 30 milliseconds per frame. But with WebGPU compute shaders, you can simulate 100,000 particles in under 2 milliseconds. That is a 150x performance leap. 150 times faster in both scale and speed. And the data never even has to leave the GPU memory. It's just an incredible testament to the power of doing the right work on the right hardware. Now, you might be wondering, how hard is it to actually write these shaders? Historically, writing GLSL shaders meant dealing with cryptic, vendor-specific errors with absolutely no stack trace. It was incredibly frustrating, a real headache. But now, developers can easily harness this new power with tools like TSL, the Three.js shading language. TSL basically replaces those raw, messy text strings with modular, type-safe JavaScript nodes. So if your shader fails now, you get standard JavaScript stack traces pointing to the exact line of code.
It's finally bringing proper IDE support, autocomplete, and modularity to GPU programming on the web.
That brings us to Section 3, the killer app. The crucial point here is how these compute shaders are unlocking the most exciting modern application possible: local AI inference. Looking at the AI inference stack, you can clearly see exactly why WebGPU has become the modern cross-platform default over legacy WebGL or CPU-bound WebAssembly. Right now, there is a massive industry push to bring machine learning models to the edge, meaning running them locally on user devices. WebGL is essentially in maintenance mode for AI at this point, and WebAssembly, while it's great, is still bound by the CPU. WebGPU steps in as the high-performance standard that just runs universally. And on platforms like Windows, we're even seeing things like WebNN, tapping directly into dedicated neural processing units, or MPUs, for even better power efficiency. It's wild.
The implications for AI applications are just staggering. By running tools like Onyx Runtime or Transformers.js locally via WebGPU, your application's data literally never hits a corporate server. This unlocks a whole new era of privacy-first applications. You can bypass GDPR compliance headaches entirely because, well, everything stays on the user's machine. You get zero network latency, responses can hit in under 50 milliseconds because you aren't waiting for a round trip to some cloud server. You eliminate those massive GPU server infrastructure costs, and your AI tool can function completely offline.
Because of this incredible local power, modern apps are adopting a brilliant hybrid architecture known as speculative inference. Here's how it works. You run small, highly quantized, super optimized 4-bit or 8-bit models right in the browser via WebGPU to give the user an instant response. We're talking perceived latencies of under 100 milliseconds. Then, if the task requires deeper reasoning or more heavy lifting, the app can seamlessly escalate that secondary task to a heavier cloud model in the background. The user gets immediate feedback, and you save an absolute fortune on server costs. Best of both worlds, really.
All right, moving on to Section 4, the horizon. The WebGPU standard is definitely not stopping here. Let's look forward to see where this technology is heading next. The WebGPU trajectory shows rapid, aggressive evolution. We have the core API and compute shaders today, right? Well, we're already seeing subgroups rolling out. These allow threads within a GPU wave to communicate directly with each other without using shared memory, which speeds up calculations up to 10x for certain operations. Moving into late 2025 and 2026, we are looking at mesh shaders. Those are going to allow for incredibly efficient GPU-driven rendering pipelines and procedural geometry without constant CPU round trips. And by 2027, there are already early talks of hardware-accelerated ray tracing making its way into the spec.
But the critical prerequisite for all these upcoming 2026 and 2027 features is something called bindless resources. Right now, accessing textures and buffers requires strict, explicit bindings. It's a bit rigid. Bindless resources will remove that friction completely, allowing the rendering of massive scene graphs, highly dynamic material systems, and arbitrary object counts. This is the exact piece of the puzzle required to make features like ray tracing acceleration structures an actual reality right inside your browser. So, to wrap this explainer up, WebGPU has successfully bridged the gap between native, low-level hardware and the frictionless distribution of the web. It's a fundamental paradigm shift that totally democratizes access to GPU compute, whether that's for interactive, terascale scientific visualizations, next-gen gaming, or privacy-first local AI. The bottleneck has been completely removed, which leaves us with one final exciting question to ponder. A supercomputer is now in every browser. What are you going to build with it?